Already, okay, very good. Okay, thank you very much. Oh,
So, so the next speaker is Ariel Zhitnitsky, and he will talk about Axion quark nugget dark matter model. So please.
okay, so let me start and see how it works. Okay, essentially the main point I'm going to do is to review some not very recent paper, but some old papers and some recent papers, and you will see precisely exactly what I want to say after a couple of slides. So essentially, first of all, the motivation. To me, it is 100% the most important part. So essentially, the most important part for me is the following, that normally when people come to the conferences, they say that it's a dark matter and that's baryogenesis, or they discuss as a two completely different sides of the stories. Just we definitely know about dark matter for many years, we definitely know about baryogenesis. But there are, in addition to that, there are so many observed puzzle, mysteries, events, and I want to mention about these puzzles today. So, and at this moment, I want to discuss only one single, some kind of very mysterious part of the story, that why visible and dark matter are so close with each other. It's not the only mystery and not the only puzzle, but I start with that as some kind of motivation. So you know exactly this part of the story, dark matter, there is nothing to discuss. And you definitely know this part of the story. Baryogenesis, again, I don't want to mention any items, it's so well known. Okay, so essentially the old paradigm. Old paradigm says the following, that dark matter requires new fields. For example, weakly interacting massive particles. Nothing is found so far. And I'll show the next slide in a couple of minutes. And naively, we would say that new fields must be non-baryonic. We know definitely what hadrons are. We know quarks, gluons, we love, and they must be something else. Why? Because we have some constraint from Big Bang nucleosynthesis. We know just decoupling dark matter from radiation during structure formation. We know that. I don't want to discuss that. So essentially, I'm talking about a completely different new paradigm, and instead of new fields which we normally discuss, for example, WIMPs, I'm talking about it could be the same quarks and gluons, the same quarks from QCD and gluons from QCD we love. Instead of baryogenesis, it could be some kind of separation of phases, like liquid and gas. At theta at theta is non-zero, it could happen. That's exactly the main motivation for the project, the proposal I'm talking about. So first, I want to show 40 years old story with the old paradigm. That we definitely see that every year we have actually better sensitivity, and we have not found anything already for 40 years. And previously it was factor of 10 every 6 years. Now it's a little bit slower. Nevertheless, in just many different instruments and detectors right here, and we don't see anything. And that's first part of the story. So essentially, the claim I'm about to make is the following, that actually we have been witnessing a manifestation of the dark matter beyond the gravity for many years. Many puzzling observations at all scales, including Big Bang, including galactic scale, sun scale, Earth scale. So today I want to discuss just some manifestations at 3 different scales, at just galactic scale, solar corona scale, and recent observations with Anita. And I also want to discuss something what's happening with CAP analysis, some kind of daily modulations, but I I'm not allowed to show any slides, but nevertheless, I will mention something. Okay, so the idea that dark matter is not necessarily weakly interacting massive particles or some kind of new fields has been known for years. Old generation like me or Pierre, we know that. So essentially it was long ago when people suggested it could be conventional quarks and conventional gluons, so-called quark nuggets, which actually exactly the dark matter, because they're in different phase. For example, the quark matter phase, not necessarily exactly like protons, like hadrons, we know. So the most important part for cosmology is definitely sigma to m. So essentially, that's exactly what enters all your cosmological observations. And for nuclear matter, you can compute it. It's an extremely small number, 10 to minus 10. So in terms of cosmology, nuclear matter portion of nuggets would be absolutely perfect dark matter. That's exactly what Witten had in mind. Nevertheless, again, old generation remember what happened after Witten suggested that in the 80s, that there is no first order phase transition. I am a QCD person. I know exactly how it happened when people realized that there is no first order phase transition. I can remember exactly when people discuss this faster evaporation. Stability is a big problem because once you actually do QCD computations, you definitely see chiral condensate, gluon condensate. You know exactly the way how they depend on temperature. It would be very fast evaporation. So there are many problems, including cosmological problems with neutron stars. I don't want to discuss that. So essentially, it was given up at 90s. Nevertheless, there is a new part of the story. It's related to the axiom. So essentially, the point is the following. There are two new elements when axion field is included. And in this case, there is a CP violating part of the story when theta is non-zero. And the second new element in comparison, what actually Witten discussed in 80s, is that it could be not necessarily nuggets, it could be anti-nuggets, but as long as these anti-nuggets, they're just normal conventional quark matter, again, they just could be absolutely dark matter. And if you accept the idea that everything comes from QCD, in this case, dark matter and visible would be the same order of magnitude, does not depend on theta, does not depend on the axion mass, does not depend on anything. It is an absolutely generic feature of the construction. Okay, so essentially the point is the following, that these nuggets are absolutely stable objects, and they behave exactly like dark matter, exactly what actually Witten discussed in 80s. And they're exactly stable because they just only very small part, fraction of them get annihilated during the long history of the universe evolution. Very small part. Okay, so that's some kind of introduction. Now, I must say the following, that right now I'm talking about that every discussion, every application I will be talking about today does satisfy all satellite, astrophysical, cosmological, and observation on Earth if this baryon charge is sufficiently large. Nevertheless, actually, I have a number of papers written about formation, about the QCD portion of the story. I will not discuss that. I have actually extra slides. If some people want to see exactly what is a formation, how separation of charges happen, I can show a couple of slides. Actually, there are some kind of experimental support for that, because this idea actually started long ago, and we wanted actually to see if at Brookhaven it can be tested. The answer is yes, it can. Okay, now let me show precisely what I'm talking about in Axion quark nugget. It's actually quark matter. It is a normal nugget, exactly the way how actually Witten discussed new phase. But there is an additional axial domain wall. Again, it's so-called n=1 axion domain wall. I don't want to discuss right now inflationary scale, Peachy-Quinn scale. Again, it is actually in extra slides. I can discuss that, not now. And the reason why it is absolutely stable, because actually equilibration between Fermi pressure and domain one pressure. So the point is the following: there are actually a couple of non-trivial structures here. There is an Axion structure. There is a related to the quark matter structure. But nevertheless, once some kind of anti-nugget enters some dense region, for example, some galaxy, center of galaxy Earth, in this case, the annihilation would happen. And there are some kind of observational evidence that it is exactly what actually happened. So essentially about new paradigm, it is a strongly interacting object. So it's not weakly interacting, strongly interacting. In this case, the question is the following: why we don't see it in everyday life? The answer is the following. For example, one WIMP with a dark matter, you have one WIMP in a liter, if it is 100 GeV. But this Axion quark nugget, AQN, I call them, it is actually 1 per 1,000 cubic kilometers. So it's essentially a huge volume. You have very, very rare events. Nevertheless, I want to actually show a couple of slides to argue that we do see such kind of rare events related with the strong interactions. And people in different labs, they say some kind of mysterious, puzzling, anomalous, exotic, you name it. But nevertheless, I'll show that just there are something very unusual. So the basic picture I want you to see is the following: that everything is quark and gluons, nothing but quarks and gluons. And when you want to say that Higgs contribute to the just now LHC people, Higgs actually produce our mass of our particles. Wrong. Proton mass comes not from the Higgs. Proton mass from QCD. It is not related to the Higgs whatsoever. So, and the reason why actually you have more or less the same dark matter and visible matter, that you have nuggets and you have anti-nuggets, but you do not have the same amount just because of the CP violation. And if this ratio, because of strong CP violation is order of 1 effect, you have 3 portions here, 2 portions here, and what's left, it is a visible. So the total baryon charge is 0. As I said, there is no baryogenesis, but nevertheless, the ratio between visible, what we are, and this is a dark, it's 1/5 or something like that. So essentially the point is the following, that it is not some kind of fine tuning. It's never been a fine tuning. So I pick up 3 papers for different scales: galactic scale, solar corona scale, Earth scale. I could actually have different examples, and I have papers with different mysterious exotic events, but I want to discuss just three these different scales. First, I start with a mysterious cosmic diffuse UV radiation. So essentially, again, I'll show a couple of slides, and what people observe the following: that they discuss, they analyze diffuse UV, far UV radiation, and unusual features of this UV radiation is the following: that it is a very, very uniform in the northern part and the southern part of galactic hemisphere. And another very unusual feature, that it is actually longitude, again, very uniform. Why it is so unusual? The reason is very, okay, so why it's so unusual? So in just in one slide, let me just list all the unusual properties. That there is a galactic latitude puzzle as well, because essentially you are not supposed to see exactly what they observe. I'll show exactly the picture from this Henry paper. And not correlation puzzle, because people normally say that what UV radiation we see in galaxy is supposed to come from UV emitting stars. And it is not precisely what we observe. We do not see a correlation between the two. And picture is dramatically different from thermal radiation. So let me show precisely what it's from Henry paper. So blue, it is the northern part, red, it is the southern part, and FUV, far UV, which Henry observed and other people, that it is a black. So you can see that the blue on the northern and southern, very different. Red, northern and southern, very different. And it is for thermal, and thermal definitely follows the UV emitting stars. Why is that so different? Because you can see exactly the way how stars are localized. Because again, red and blue is northern and southern, and you can definitely see it is not uniformly localized along hemispheres. So what's actually happening for thermal, which is actually related to the dust, it does follow conventional star localization. But what they observe actually for far UV, it is not something which follows the stars. It's very, very symmetric. It is dramatically different from conventional star localization. Okay, so essentially the way how I can understand this property is the following. As I said, everything is related to the nuggets. Can you imagine you have nuggets, you have anti-nuggets, and when these anti-nuggets propagate in the galaxy, in this case, annihilation does happen. Annihilation happens with the conventional baryonic material which you have in the galaxies. And in this case, they emit electromagnetic radiation. And again, I can compute the temperature of these nuggets. Why you have a non-zero high temperature? Because you have annihilation, you have a thermalization inside, and after that you have emission from so-called electrosphere I show. Again, computations can be done here. And the typical temperature for the density about just 1 per cubic centimeter, for the typical density in galaxy, you have temperature in the region 10 eV, such that far UV and UV actually can be emitted. So that's exactly the point. Now, again, I know exactly what is the dark matter. What is the density? I can compute what is the total intensity will be emitted from all these nuggets. I do the computations and I see something like 10 to minus 5 erg per centimeter square per second. That's very, very close to Henry and other actually observed. If you do conventional beams definitely also actually can radiate something because of annihilation, but you have 12 orders of magnitude smaller than actually what they observed. Again, just huge difference. And in this case, all these puzzles I mentioned about uniformity, galactic latitude, galactic longitude, non-correlation with you emitting stars, definitely all these puzzles are immediately resolved. Okay, next mystery I want to mention today, because I don't have much time to discuss many others. Nevertheless, I want to mention about the solar system. Again, about extreme UV from the sun, we know for 80 years. It is a mystery. Why is it a mystery? It is a mystery because what we observe a temperature which is 1,000,000 degrees in corona, which is 2,000 kilometers above the photosphere. And normally you say, okay, density is getting smaller and smaller, temperature is getting smaller and smaller. It's not actually what has been observed. It has been observed that the temperature suddenly drops, not drops, increases 2 orders of magnitude in magnitude. Let me show precisely the way how it goes. So that's 2,000 kilometers, that's corona. That's temperature, that's from photosphere. We definitely know 5776 degrees from the photosphere. So just we know very well. Now, suddenly, on the level of 100 kilometers, no more than that, you have increased 300 times for the temperature. So again, this is a very beautiful part of the story for the thermal. And here is soft X-rays and extreme UV. And the width, it's not more than 200 kilometers, it's less. That's exactly the way how people call this puzzle, heating puzzle. So the way how Parker wanted to resolve this puzzle, again, it's very nice and long story, but before I get to the story, let me formulate essentially what people observed. People observed the following, that the puzzle, that everything, as I said, happens on the scale 200 kilometers. It's very sudden, that just right here. It's right here. And, oh, sorry. And we definitely compute approximately what is, can you hear me? Yeah. And it's happening with intensity approximately 10 to 27 erg per second. It is definitely much smaller than our emission from the sun. It's something like 10 to minus 6 portion, but nevertheless, we observe it in soft X-rays and we observe it in the extreme UV. Important part, that it is a very, very uniform. Please remember that. And it does not depend on the solar activity whatsoever. It does not depend on magnetic activity whatsoever. It does not depend whether you have active region or you don't. So now, so essentially this proposal is the following. What's happening is the following. Dark matter anti-nuggets that come to corona get annihilated, and this is a new source of energy. And the story is the following. You can compute this part of the emission just in one line. That's exactly the line. You compute how many dark matters enter, they annihilate, you know exactly the amount, and you get exactly 10 to 27 erg per second. Can you imagine how I was actually, it was mysterious for me. I'm computing from dark matter particles. Nevertheless, I get 10 to 27 observed in X-rays known for many, many years. Now, the important portion here, that essentially it is extremely uniform. It cannot depend on magnetic field activity. It cannot depend on solar activity. So all these 11 years, you get exactly the same amount of dark matter. That's exactly what people observe with soft X-ray. Now, I want to make some kind of historical remarks. It has been known for years that that's exactly what soft X-rays and extreme soft X-rays. It has been known from the sun. And what Parker suggested at this time, he suggested to introduce nanoflares, just pure theoretical construction. And the way how he introduced it, he said, it is my conjecture that you have a flares because of the magnetic reconnection. You must have some kind of the same flares, but at a smaller scale. You have some reconnection around the surface everywhere, uniformly distributed. And that's the way how he introduced nanoflares many years ago in 80s. And that's exactly what he saw, that he saw that it is something like flares. But nevertheless, plasma physics on Earth, they just try to see what is actually could happen. And it is almost impossible to have any magnetic reconnections with so small magnetic field, because typical magnetic field in sun, on the surface of the sun, it's one Gauss, like here on Earth. And kinetic energy is 4, 5, 6 orders of magnitude larger than that. It's very difficult, hard to imagine how magnetic reconnection would happen with so small magnetic field. Okay, so when we did our computations, and this is already with Astra people, because I collaborate with mostly with Astra people and particle physics people, but this is with Astra people, so it is a real Monte Carlo simulations on the sun. And you see that annihilation occurs precisely just on in the width about 100 kilometers, which is a very hard to imagine for solar physics people, because the only scale they have is they have scale just few thousand kilometers. So now I'm coming to Earth from the sun. So started with galaxy, sun, Earth. So when these nuggets come to Earth, in this case, the events, it's very, very rare events. You can see that it is not like WIMPs or Axions. It's extremely rare events. Just you have one event per many, many years per 100 kilometers. So I want to compare the flux of the normal galactic axions with now, idea again, the computations can be done for the axions from these nuggets, because when nuggets come to Earth, they interact with the with the Earth's material, and they emit axions, and these axions would be actually relativistic axions. And we want to see this relativistic axions, the flux. And we computed this flux. Again, the flux for the relativistic axions, it's about 10 to 14 eV. You have to compare with just with the galactic axions Pierre is talking about, 10 to 16. So it's 2 orders of magnitude smaller for the flux. And I know about so-called cosmological cosmic axion background. I know from Nick Roth, who actually visited UBC. And this relativistic axions, the density must be smaller than CMB photons, because they're just relativistic particles. And in this case, the constraint is smaller than 10 to 10. So it's definitely much, much larger than CMB, but it is a locally, again, not globally. It's only on the Earth's surface where your instrument is. So the typical distribution, again, can be computed. It's about 0.6 for average. Now, now I come to the point about how to measure such kind of relativistic axions. And that's idea was advocated by me, Dima Butker, who is just some of you probably know, experimentalist in Mainz, and Berkeley previously, and Berkeley, and nuclear physics person who is right now, Flambaum, who is right now in Australia. So essentially, the idea is the following, that if you have relativistic axions, it is very, very different from non-relativistic axions. Non-relativistic axions, delta nu to nu, it's 10 to minus 6. So you expect in your cavity some kind of very narrow resonance, 10 to minus C, and 6, and all people try to see exactly this resonance. It's exactly what Pierre suggested many years ago, and people try to see such kind of axions. Now, these axions are relativistic. Delta nu nu is order of 1. So it's a broadband strategy must be actually applied here, implemented somehow. And another part of the story that for such kind of relativistic axions, it should be some kind of daily modulations. Even if your instrument is not sensitive to the directionality, still there is some kind of daily modulations because of the following reasons. Just let me show first about Do I have? Yeah, I have just a picture here to demonstrate what is the daily modulations. People know about annual modulations for years. They definitely know because Earth is just rotating here. That just you have a axis with respect to galactic center. That's exactly what people normally discuss, that even if your detector is not sensitive to directionality, you have to have annual modulations. Now it is not only annual modulations, it is a daily modulations as well. So, and about daily modulations, I have a couple of comments here. So normally people did not discuss daily modulations in the past. Why is that? It's very, very simple. If your instrument is not sensitive to the directionality, the velocity of the of Earth rotating about its axis, very, very small in comparison with the velocity around the sun. So essentially, it's very, very small effect, and people did not discuss all these years in the past. But here, actually, you do have that. And the reason why you have that for the relativistic axions, because when nugget enters the Earth and exits the Earth, size is a little bit different, not a little bit, 10–20% difference. And that's exactly the important effect. Okay, so essentially the way how we can measure such kind of daily modulations. The idea was the following. Okay, you have to feed your power access to this cosine, which is related to the daily modulations. And let's assume that you see the daily modulations. The way how you can do analysis, you can do Fourier transform, or you can just see in terms of time, sine or cosine. But important part here that is following. Definitely, we should see daily modulations in everyday life. Just sun comes and goes. But nevertheless, and human activity as well, it follows daily modulations. Nevertheless, there are a couple of tests which can you actually do to see that it is not related to human activity, it is not related to tides, it is not related to the power outages, it is not related to anything. And for example, you can do B = 0 test, and in this case, you must not see the daily modulations. You can actually see the fluctuations of your temperature in your cavity. You must not see the daily modulations. So there are many, many different tests and checks that what you see is a real physical phenomena. Okay, so a couple of comments about the relativistic axions, because it's very, very different in terms of the treatment from everything what we normally do. In this case, normally, when we discuss what is the probability for the conversion, it is proportional to L², where L it is the size of your instrument. But it is correct as long as actually the size of your instrument is much smaller than lambda de Broglie wavelengths. If it is not the case, in this case, the correct formula that it is not L² but L times L small, which is actually a correlation length. Another part of the story, and something what just we discussed with Yanis, that if you have velocity close to C, in this case, the formation time, it is not the formation time of your instrument, de Broglie length. It is actually a Compton length scale, which is a much shorter. So that's very important when you actually discuss and do the computations. In this case, you can excite in cavity many, many different modes, highly excited modes. Normally, you don't care about all these modes, you ignore them, but you cannot do that now. The same with the formation length. Formation length, it is not scale of your instrument, the scale is actually Compton length for velocity. Now, work in progress. I was hoping to get some kind of slides to show what's happening with cast cap analysis, what we are doing right now. I have not permission to show the slides from Konstantin Zoitas, but nevertheless, essentially, we do see some kind of modulations. We don't understand the nature. Nevertheless, we actually did some tests. We did the test with the B equals 0, no modulations whatsoever. We did test with the temperature 0, non-zero, and we just do not see fluctuations in cavity. So essentially, it remains some kind of, unfortunately, cast is shut down. Just we cannot actually do any test with the cast right now. So Yanis is in the room. He knows about that, and he promised to do his analysis as well. Correct, Yanis? Okay, so essentially, I am suggesting that everyone who has any instrument which is sensitive to axions, even if it is not for broadband, it is still okay because you have to sum over all frequency bands. So that's exactly the idea. And the reason why you can get to high precision because you sum over all frequencies. And after that, you actually collect the signal during many, many days during, for example, 1 month. You don't go to a different season because actually there is actually phase for a different season. So you don't want to mess up different signals. But nevertheless, when you sum over many, many days, in this case, you can see a signal. Okay, and the last part of the story, again, about the Earth. About Anita, I mentioned that I want to show something what we observe anomalies. That there are the reason why I pick up Anita, because I know PI from Anita collaboration. But actually I can discuss Pierre Roger or telescope arrays. There are many anomalies as well. So I just prepared, I can show, but nevertheless, I want to discuss Anita. I have on time for Anita. So 2 events which had been recorded by Anita have very, very strange so-called, they called anomalous events because there is a non-inverted polarity. I'll show what does it mean non-inverted polarity in a second. Okay. That normally when you have a cosmic rays and cosmic rays, so let me just show precisely here what they observed. A, it is exactly non-inverted polarity. So you see exactly the way how it goes. Normally, what you can have actually non-inverted, you can have non-inverted polarity, but only for small angle, let's say 3 or 4 degrees. Why is that? Because cosmic rays could go actually, here is Anita, cosmic rays could go this way, and in this case, it would be not inverted polarity. But what normally people expected, that if you have angle, let's say 30 or 40 degrees, it must be actually inverted polarity because you just flip the polarity. And that's exactly what people expected. Because there is no way you can have some cosmic rays go through the Earth 6,000 kilometers. Just at least it is definitely ruled out with the standard model neutrinos, for example. Okay, so what people observed the following, just that you do have 2 anomalous Anita events, and you cannot actually fit with the conventional standard neutrino, even beyond standard model neutrino, you still cannot actually fit properly. So it's almost ruled out. I just don't want to discuss exactly precisely why is that. So, but if it is a nugget, in this case, the story is very just beautiful and trivial. You don't have to invent anything because a nugget can easily cross the Earth. And when it crosses the Earth, it definitely heats up. And let me show actually the way how normally journalists represent that. They call this odd particles. I saw it somewhere. Yeah, odd particles, odd balls. How it happened actually with the explanation in terms of nuggets. When nuggets cross the Earth, the definitely temperature is very high, up to 100 kV and even higher. In this case, you have E plus and minus definitely just produce. When you have a plus and minus inside of Earth, you don't see that whatever happens. But once it goes out, in this case, in magnetic field, you have this radio signal. And this radio signal has been computed due to this E plus and minus, which are coming out from the nugget. So we computed electric field, we computed the phases, and let me show precisely the way how computations are normally done. And it is a classical ENTM. So once you have E plus and minus, you definitely see how E plus and minus actually propagate on Earth, in the magnetic field of Earth with the 1 Gauss. And typically what we have again, non-inverted polarity. But what is important that just pay attention that electric field is measured as millivolt meter. And this is a typical nanosecond. I go back to what had been measured. It had been measured, you cannot see it, but it is a millivolt meter, and this is a typically 1 nanosecond. So the basic scale is exactly right, okay? So that's about Anita portion of the story. Now, I come to the conclusion. I don't have much time. So my conclusion is the following, that essentially every time we say non-baryonic dark matter, non-baryonic dark matter, my claim is that actually non-baryonic dark matter, it could be conventional baryonic hadronic matter we know and love, QCD. And in this case, this part of the story, it's almost a triviality because you simply cannot avoid it. It's model independent part of the story. Why is that? Because it is a proportional one and the same fundamental dimensional parameter. We know lambda QCD in just this number. And proton mass is proportional to the same number. And model actually offers simultaneous resolution of many different old mysteries related to dark matter, baryogenesis. And essentially paradigm is entirely changed, that dark matter, when enters the Earth's atmosphere, in this case, it's strongly interacting part. And the same in galaxy, when you have a center of galaxy, in this case, actually, it is a strongly interacting part of the story. Okay, there are many hints I mentioned about this, just three different galactic, solar, and Earth environment that actually suggesting that something is happening here. And but there are many more. For example, I have no time to discuss primordial lithium puzzle today. I don't have time to discuss some kind of background, extragalactic background radiation. Again, in many different frequency bands, we definitely see some kind of excess in emission. But nevertheless, there are some kind of puzzles at many different levels, including the structure formation, and people discuss such kind of problems like core cast problem, too big to fail problem, and many similar problems. So essentially, the nugget behaves like a chameleon-like composite particles. It's very large, macroscopically large, but it does not interact whatsoever at a large scale. So it's a large scale, more than 10 kiloparsec, it's absolutely dark matter. But once actually it enters more or less dense region, it definitely starts to interact in the galactic scale, on Earth and the Sun, everywhere. So in this case, the question is how it could happen that we had never observed in dark matter labs. Yes, the answer is the following. What dark matter labs do, they just search for WIMPs, which is a 100 GeV scale normally. maybe a little bit more, a little bit less, but that's exactly the main scale. Now we are talking about dramatically different scale. And therefore, it takes millions of years before any single dark matter lab would observe a single event here. On the other hand, cosmic ray labs are just perfect in terms of size, because it is 100 kilometers in size. And in this case, in principle, they could observe it. But it turns out that I communicated to many people in cosmic labs that essentially hardware and software of all these labs are designed from the very beginning, from the start, that they actually measure ultra-relativistic particles, ultra-relativistic protons. That's exactly the way how they are designed, actually. And they cut off all time scale, which is irrelevant for their studies. And I believe that there is a pure sociological problem that actually people prefer to stay in the conventional WIMP paradigm and the conventional old paradigm for non-interacting dark matter. Okay, so that idea comes from, again, discussions with Dima Butter, who actually had at the very, very last many different elephants. He calls this elephant dark matter, dark energy, baryogenesis, he had 6 or 7 elephants. Now, I believe that actually we have one single elephant, but nevertheless, we are talking about different parts of the story. So the main sense of my talk that different people in different labs around the globe, they study different experiments and different observations and different parts of the same elephant. That's my part of the story. And I am about to conclude. Do we have extraordinary evidence to make extraordinary claim? Well, time will tell. And of course, I quote Carl Sagan, which is precisely the way how it is actually was quoted. Thank you very much.
Thank you for this nice talk and questions.
Have you looked at what sort of signature this might have in ice cube?
Yeah, from ice cube, that B, which I mentioned more than 10 times to 24, comes from ice cube, precisely.
But we don't see any events.
They don't see for 10 years, that's absolutely correct. But nevertheless, the area is small enough to make.
I understand, but if you are saying the Anita events are due to these, we haven't seen. Yeah, that's exactly the constraint. B must be larger than this one, such that flux is smaller than this one. So it comes exactly from ice cube, correct? Yes, we did it. And we have appendix actually in the paper where the constraint. And because you asked this question, I want to actually elaborate about this constraint in a very non-trivial way. That this constraint comes from ice cube. That's constraint for the nugget. It turns out that if you look nanoflares, which Parker suggested 30 years ago, and the way how people who do solar physics and they model solar physics, they say, okay, right now, the way how they treat nanoflares, they say, we don't care about the physical nature, we don't care about the origin, we cannot explain, and we just model it as an injection of the energy. You know, physics people cannot do that, but astro people easily do that. And what's happening next? They have a model for solar corona heating, and they model with nanoflares, and energy from here to there is precisely the constraint I have for baryon charge. So it is an unbelievable, mysterious connection between ice cube constraint and nanoflares energy they model to feed the observation for the solar corona. Just the same number.
So maybe a very naive question. So if we take, let's say, QCD in large N, what kind of object will be this nugget?
What time?
What kind of object will be like?
Oh,
what
oh,
operate? What
when they're formation time, when they're formed.
Right, because it should.
Yeah,
it's-
okay,
it's
during the
like-
QCD phase transition, of course. When theta was non-zero during the QCD phase transition, Pierre discussed 1 GeV, but nevertheless theta was non-zero up to the chiral phase transition 170 MeV. And in this case, what's normally people are talking about, people talking about how theta is actually oscillating and relaxing to whatever value it is today. But nevertheless, it was not zero from the very beginning. Exactly at that time, separation of charges could occur. I prepared the slides, I can show the slides, does not matter the slides. But nevertheless, exactly at that time when theta was non-zero, some can be produced nuggets and some can produce anti-nuggets because of CP violation, okay? And the number, not number, the size is different. So if size original was different, after that evolution tells you that actually the total baryon charge hidden in nuggets and hidden in anti-nuggets would be different. So what is the difference? The difference is order of 1, always. So after that, the evolution goes just as a normal way. Annihilation is happening from 170 MeV to approximately 40 MeV, when all anti-protons are actually get annihilated in the conventional baryogenesis picture. What Sakharov suggested many years ago, he said, we have to have 0.1 more baryons. What I'm suggesting, we do not have this 0.1. We have different size between nuggets and anti-nuggets. And how many baryons we have? It's precisely the same difference between the baryon charges inside of nuggets and anti-nuggets. It is always order of 1, always, no matter what. But it happens during the Big Bang. And after that, you can see actually what's happening with the evolution. And for example, the next one, during QCD phase transition. When you have Big Bang, it is a 1 MeV scale. Again, you can see what happens to these nuggets. The answer is they survive, and they not only survive, they can resolve so-called primordial lithium puzzle exactly at the same time without single modification of anything.
That's precisely my question. Like at zero temperature, how they?
It's not zero temperature, just zero temperature is today.
Today, let's say today. How
Yeah.
they can, like what kind of objects they are in QCD spectrum? If you consider, for instance, if you look from the perspective of large N, for instance, we know what are the baryons or the mesons. So what kind of operator is that? Like, because
It is not local operator. That's exactly the point. Just normally people in the community, they say, we want to see the local operator, the local. It is a not local object. You have 10 to 25 quarks. It's not a local operator. It's not a local field. It is like condensed matter system.
like hydrogen atom, for instance, in electrodynamics, but it still can be written as a pole.
Yeah, hydrogen you can, but if you have a nuclei with a number of nuclei 10 to 25, you cannot do actually local physics. It is a complex condensed matter physics. And that's the way how we study. That's the difference between the conventional picture when you have you want to have a local operator and you say, I want to see the local operator to do my computations. The answer is, I am a QCD person. I like local QCD, but nevertheless, it is not what you can do here. You have to know condensed matter to do that.
Thanks for the talk. I think I'm still stuck at the very beginning. So I'm wondering
That's
if you
good.
can help me understand how these form, how these.
Okay,
form.
yeah,
And I guess like a question along those lines, maybe help me
Okay.
understand. If you didn't have the Axion, but you had I'm confused because there's no first order phase transition here. So if you didn't have the Axion, you had just a constant theta bar parameter that happened to not be.
It's
zero.
not constant, just, okay, let me,
But you
okay,
formed
because
the-
you are asking the question about the formation.
Yes.
Would
I
you,
wanna understand the formation.
would you like me to show a couple of slides I prepared? for the formation.
Sure.
Okay, yeah, just I go ahead and show. That's backup slides I prepared because just people like you definitely ask the question about formation. Let me show and let me just formulate some kind of misconceptions people always have. So for example, people say topological objects cannot be formed if inflation happens before actually pitch queen. Wrong, it's incorrect. And the reason is for n equals 1 domain walls, because it is a conventional soliton, which is a form in a beautiful way. And you know from Sine-Gordon model, you know that from, so it is a, let's say 2 pi, it is a 0, and the interpolation between the two always happens and does not matter is it pitch queen before inflation or after inflation. It's so-called n equals 1 because this vacuum and this vacuum, it's one and the same vacuum. It is just one and the same physical vacuum. And inflation never ever separates these two of them. And there are two arguments, just I have two arguments in the original paper. So essentially the first argument that again, condensed matter people know this well, particle physics know that not so well, that there is so-called bosonization. So this soliton, which is actually interpolation, exactly the domain wall interpolation between 0 and 2 pi, can be formulated in terms of the local field. And local field cannot be actually removed by inflation. It must stay the same. So all these domain walls, like the solutions in the Sine-Gordon, they stay no matter what. Yeah, okay, so coming back to your question. So essentially the formation can be explained. And again, I have couple of specific computations, the way how this closed domain wall form, and Pierre and Vilenkin computed this closed domain wall many years ago in 80s. And they say, okay, just eventually what is happening, they actually collapse and produce some axions. What I am saying that if you have inside quarks, in this case, they do not collapse. There is a Fermi pressure and there is actually axion domain wall pressure, and you have equilibration. And I explicitly demonstrated that there is no, they do not collapse. They form absolutely stable configuration, which I call axion domain wall, axion quark nugget. So that's the way how form, but nevertheless, there is a very, very specific, it's just 3 or 4 papers with the specific computations. It's not just pure QCD computations. Essentially, it is a condensed matter computations with strongly interacting system.
Okay, thank you. Okay, so I think we should move on and continue. Yeah, yeah. Ah, okay. Oh, in half an hour, 20 minutes. 20 minutes.